In section 3.5, we're looking at how parallel lines relate to triangles, and we're going to use parallel lines to prove theorems about triangles, and then we're going to find measures of angles in triangles. And something they start out with is thinking about the measures of the angles in a triangle. Now, if you draw any triangle, cut it out, and then you tear off the corners so that you can kind of put them together, and then put all of those corners together, then when you put that together, you should notice that it's forming a line. And if that's forming a line, then we should be able to conclude that that's adding up to 180 degrees. Now, before we go further with that, I'm going to talk briefly about the parallel postulate. The parallel postulate tells us that if we have a point and we have a line, if we want to make a line parallel to this one that crosses through this point, then there's exactly one way we can draw it. We can't get more than one and say that they're both parallel. There's exactly one line that passes through there. Now we're going to use that for proving what we just showed about the triangle. Notice here I have a triangle. I want to show that the angles add up to 180 degrees. And the first step that I'm going to do is use that parallel postulate. The parallel postulate told me if I take a line, in this case I'm going to use AC, and I want a line parallel to B, I can do that. On Sketchpad, it's easy just saying construct a parallel line as long as I've highlighted the line and the point not on the line. And now this line, even if I move C, it's always going to be parallel. Now if I measure those angles in here, notice how angle C will always match up there, angle B always match up above, so that my angle C here, because these are alternate interior angles, will always be equal to each other. Angle A also has an alternate interior angle up here. So basically what I'm saying is I've got angle A, angle B, and angle C. When I add all of them together, I'm going to get this line, which is equal to 180 degrees. Even if I move my triangle, this will still be the sum of angle A, angle C, and this angle here at B. And so from that we can conclude the triangle angle sum theorem. Basically, that the sum of the angles in a triangle is 180 degrees. Now we're going to look at the proof of this. To do that, we're going to draw what's called an auxiliary line. An auxiliary line is when we're adding something to our proof that we're constructing it in such a way so that we get some kind of desired characteristic. Here we want the line to be parallel. So if we use our parallel postulate, remember that said if we have a line and a point not on the line, so I'm going to be using B up here, then we can have exactly one parallel line. So there's no confusion here when I draw this line PR through B that it's parallel to AC because I constructed it that way, and there's only one possible line that can do that. Now the next thing I'm going to note is a supplementary pair here. Now for a linear pair, remember that a linear pair, or when we talk about supplementary angles, that's two angles. So they're actually talking about P, B to C, paired with angle 3 here, saying that they're supplementary because they're a linear pair. Because they're a linear pair, they add up to 180 degrees, and that's our definition of supplementary. But what we want is to get angles 1 and 2 in here. Notice that PBC is made of angles 1 and 2, and we can do that because that's our angle addition postulate. The parts add up to the whole. Next, we'll do some substitution here where I'm taking my PBC from here, substituting in 1 and 2 instead of angle PBC. That's just a substitution. And then I'm going to do another substitution here after I notice that angles 1 and angles A are congruent because of these being parallel. These are now alternate interior angles. So 1 is congruent to A, C is congruent to 3. When we have congruent angles, we know that their measures are equal to each other. That's our definition of congruent angles. And then we can substitute in to get what we were looking for, that those three angles add up to 180 degrees. Notice then that those are the three angles inside of the triangle, angles A, angle 2, and angle C. So knowing that angles add up to 180 degrees inside of a triangle can help us with a problem like this. But notice exactly where our angles are. If I look at this, in this triangle over here, BDC, I might not be able to solve this for y right now because I have two variables. But in the smaller triangle, BAD, I have a 43, a 59, and x. And so I can solve that by adding those three angles and knowing that they're equal to 180 degrees. And that will come to 78 degrees. Now if I'm going to find y in this picture, well, I don't actually have to use the triangles now. I should note that this is forming a linear pair. So x and y are going to add up to give me 180 degrees. Simplifying that out, I'll find that y is equal to 102. Notice I'm substituting the x that I found in the first part of this problem. The next thing we look at are the exterior angles. Now this could be for any polygon, but right now we're looking at triangles specifically. The exterior angle is if we extend the side coming out, and that angle out here will be the exterior angle. The remote interior angles then are the ones across from it. So it would not be this angle here, angle 4. That's not a remote interior angle, just the ones that are across from it. Now if we look at these angles in Sketchpad, we might notice something about them. If I move this around, I'm measuring A, I'm measuring B, and I'm measuring angle C. Notice what happens when I add angles A and B together, comparing that to the measure of this angle, this exterior angle at C. Notice that even as I move this around, the numbers all change, but these two sums remain the same. This leads to another theorem that we have. This is the triangle exterior angle theorem. What this is telling us is if we look at the angle on the outside, angle 1 is the exterior angle, and we compare that to the angles on the inside, but not touching it, the remote interior angles, that they'll have the same sum. The proof's pretty simple. If we look at the triangle angle sum theorem, we should note that angles 2, 3, and if I add another 4 here, then those angles are going to add up to 180 degrees because they're inside of a triangle. If I look at angles 1 and 4, we note that they are a linear pair supplementary, and so they also add up to 180 degrees. Now since everything's adding up to 180 degrees, I can substitute this angle 1 and angle 4, their measures can go in for 180, and then I can subtract that angle 4 from both sides. The measure of angle 2 plus the measure of angle 3 is equal to the measure of angle 1. Now if we wanted to use this theorem, we're going to do it like this. We look at the relationship, we notice where the angle is. The outside angle is equal to the sum of the two remote interior angles. So since these are the interior angles, they're going to go here and here, giving us that the measure of angle 1 is 98 degrees. In this problem, notice we're only given one remote interior angle and one exterior angle. So when we set up this, we'll notice the exterior angle, 124, is equal to the sum of the interior angles. So my interior angles would be the measure of angle 2 plus this 59. And so I'm going to subtract 59 to solve this problem. And that comes to 65 degrees. This problem could also be used in this. Here's another application of the problem. We're talking about a radar that's seeing a ghost image down here. But mostly observe the triangle that they have here in this problem. When we look at the angle x coming out of the radar tower and the angle that the airplane makes with the ground going up to the radar tower, then we can see that this is just another case of remote interior angles with the exterior angle. So we should notice that the 80 is equal to x plus 30 because the x and the 30 are in the inside, leaving us with x is equal to 50 degrees.